All right, let's talk about similar figures. Now, a few years ago, probably around 8th grade, you would have done a math unit on transformations. You would have seen reflections and rotations and translations or slides. And all of those transformations change the position of a particular shape, but it didn't change the shape itself. We call those kinds of transformations rigid motion. We can also call them isometries. Remember, it changed the position, but not the shape. So those two shapes, we call those congruent. Congruent is a new definition for your notebooks today. And congruent simply means same exact shape, same exact size. It can be in a different place on your graph altogether, but it needs to be the same shape, same size. Then you did a fourth kind of transformation called a dilation. Dilation can be either an enlargement or a reduction. So the shape almost stayed the same, right? It was the same shape, but it simply changed size. When we change the size of the shape, but the shapes are identical in every other way, we call those shapes similar. So similar in your notebooks, you need to write that as same exact shape, but a different size. Now, one of your responsibilities taking away from this video is you need to know the difference between congruent and similar. So let's take a look at these shapes really quickly. Let's start with the yellow rectangles. Are they congruent or similar? Those are congruent. They're exactly the same shape, same size, just one's been rotated. The blue arrows are similar. The orange starbursts are similar. And the pink pentagons are congruent. Make sure you know the difference between congruent and similar. So in similar figures, we say that these shapes are proportional, right? Which means that we're going to take and use a scale factor to take us from pre-image to image. So that scale factor applies to our side lengths, right? If I take this smaller trapezoid as my pre-image and the larger one as my image, looking at all the different sides or coordinating sides, you can see that the side lengths have been times by a scale factor of 3. 4 goes to 12, 2 goes to 6, 6 goes to 18, and so on. Similar shapes, I can't say that enough, they have to have proportional sides. So to decide if two shapes are similar, I need to check that they all share the same scale factor. So if I look at coordinating sides on these two triangles, in my image, right, the smaller one is my new image, new over old. I check 4 over 8, and that gives me a scale factor of 0.5. I can check the 5 over 10, and I can verify that it has a scale factor of 0.5. And 6 over 12 gives me that same scale factor of 0.5. If these did not have all the same scale factor, these shapes would not be similar. I want to show you just one more thing with similar shapes. First of all, the larger one is my image, the smaller one is my pre-image. So if I look at all my different sides, I can verify that my scale factor is 3, right? 18 divided by 6, 9 divided by 3, and 18 divided by 6. Again, of course, all of those have a scale factor of 3. I would need to check all 6 sides on my hexagon to verify that all 6 sides share the same scale factor. But that's not the only thing that makes these two shapes similar. I'm going to pull our smaller shape over here and show you something really quickly. If I compare angle measures on my two similar shapes, you can see that all 6 angles aren't proportional, but equal, right? My angles are congruent. So, let's talk about how to verify that two shapes are similar, how to prove that two shapes are similar. You must show that all the sides, all the corresponding sides, have the same proportion, that all sides are proportional, and that all angles are congruent. We're actually going to be using protractors to measure our angles to verify that they're all the same measure, and we'll talk a little bit more about that in class. One last thing before we wrap it up today. Similar figures can help us solve a lot of issues in the real world, one of which is, to find heights of really tall structures. You can't exactly pull out a tape measure and measure the height of a building. That would be too hard, right? So people use proportions to help us measure things that are too big to measure. So I can use a proportion. I'm going to use the proportion height over shadow length, right? I have this 6-foot tall man casting a 4-foot long shadow. And at that exact same time of day, this X foot tall building is casting a 30-foot shadow. We can set that up as a proportion. I can set this up a number of different ways, but I'm going to choose to do height over shadow length. For the man, that's 6 over 4, right? Height over shadow length. And for the building, that's X over 30. And just a reminder that to solve proportions, we use cross products. When I multiply my diagonals, one diagonal gives me 4x, the other diagonal gives me 180. And when I divide both sides by 4, I find that the building is 45 feet tall. So taking things that I can measure and helping or letting them help me solve something that I can't is one way that similar figures are used in the real world. All right, I think that's probably enough for today. Bring me any questions you have so far. Make sure you have your notes on distance formula because we'll actually be using those to help us find side lengths on this next assignment. Don't forget to take the attached quiz, and I hope you have a fantastic day. I'll see you next time.